And the lecture today is called Learning Structure Predictors. So let me introduce that. So normally so this is supervised machine learning. Normally when we get introduced to supervised machine learning, we're given training data, pairs of input-output points, x, y, a bunch of them. And we want to learn a predictor that goes from inputs to outputs and that works well on new inputs, okay? So that generalizes, okay? So here, I just say works well, and then there's a whole theory behind what does it mean to work well and what are the guarantees that a predictor that we learn will work well on unseen inputs, okay? But what I want to focus on here is the type of outputs that we have, the type of Ys, okay? So normally, when we're introduced to machine learning, almost all the courses focus on binary prediction, where Y is just a sign, positive or negative. Is it a positive example? Is it a negative example? And we have to focus on this binary choice. Okay, and then there's a natural extension from that to multi-class prediction, where the output is one of a set of fixed values. Okay, so for example, in text categorization, we'd like to classify text into politics, sports, economics, and so on. Okay, so we have, but these values are atomic. It's just this value or the other. Okay, so when we talk about structured prediction, what we mean by that is that the outputs are structures, so they are not atomic anymore. And so depending on the type of output structure, we have different types of machine learning problems. Okay, but there's a whole set of techniques that applies to any of them. Okay, so for example, for sequence predictions, what we predict are sequences, and for syntactic parsing, what we predict are trees that represent the syntax. Okay, so note that here I'm talking about the output. Okay, I'm not talking about what's the nature of the input, which in structured problems it's usually also a structure. Okay, but what makes so after all, this will be an extension, okay, from binary to multi-class to structured outputs, okay? And so what makes this unique is the type of output, okay? The type of, well, the inputs are structured is also relevant, but it's not the main focus today, okay? So let me give you some examples in the context of natural language processing. So one very typical example of such tasks is name entity recognition, which very generally, so we're given an input X, which is a sentence maybe, like, which we see as a sequence. And what we want to predict is a sequence that encodes whether there are name entities in that sentence or not. Okay, so we have, for example, that Jim is labeled as a person, and that 300 is labeled as a quantity, and Arme Corporation is labeled as an organization, and this is a time expression. Okay, so in this case, if we go into the definition of this problem, and you will find many, so we could see that we're given a sentence, which is a sequence, and for each of the words of the sentence, we have to predict one label that encodes whether there is an entity or not. Okay, so these are labels, but this is also a label that says there is no entity here. Okay, but we look at this problem as not predicting one tag for each word, which it is, but actually today we'll look at this as we're given a sequence and we want to predict another sequence. Okay, so the output is not each of these individual things, it's the whole thing. Okay, and so in NLP the problem is ambiguity. Okay, so London is a city. But in this sentence, London is not a city, is a last name of a person. So it's a person, okay? So Jack London went to Paris, and maybe the next sentence is Paris Hilton went to London. So we need to do something to just disambiguate that. So maybe we have prior knowledge that Paris and London are cities. But we need something that can predict that in this context, this thing is a person, and this thing is a person. Okay, so how are we going to do that? Okay, so what we're going to do is to learn predictors that exploit the context of things. Okay, because looking at the context, so if we look at this thing, here's a verb, went. So who is going? What are the things that go to places? So these are people that move. Okay. So this must be a person. It cannot be a location. Okay. So in this position, we expect people or things that move. Okay. So we need to learn predictors that somehow have this expressivity. Okay. But when we talk about structure prediction, what's going to be relevant is not just that things depend on the context, because here there's going to be two contexts. Okay, so if we look at just the tags here, okay, we can look at as I just say, we can look at the input context. So there's a verb here. Okay, so this is an indication that this is a person. Okay, so this is the input and this is given. So we can exploit the context of the input. But what's going to be relevant is to also exploit the context of the output. Okay, so because, for example, so we may know that Jack is a person name, and things that, so it's labeled person. And because names have multiple components, so anything that is capitalized and follows a person name is likely to continue being a person name. Okay, so the fact that London is after this person, this tag of person, indicates that this is also a person. Okay, so here there must in the data here there must be statistical dependencies between this word and these tags, but also between these two tags. Okay, and so this will happen all the time. Okay, so what we want is to have machine learning methods that are expressive enough to capture dependencies both in the input and in the output. Okay, and what's going to be challenging is to exploit the dependencies on the output, because the output is something that is structured, so it's a sequence of stacks, and we don't have it at the beginning. So we have to predict it. We'd like to predict it all at once and exploit those dependencies, but that's going to be computationally challenging. So what we're going to do is to see techniques that can exploit these things while being computationally efficient. Okay? There's many other problems. So this is a huge family of problems, and actually most problems that deal with real data have a structured nature. Okay? Because data in this world is structured. Okay? So this is another problem that is a bit intermediate within NLP, which is part of HV tagging. Again, we're given a sentence, and we want to label each word with a syntactic category. So noun, noun, verb, noun. So here again, place. In most cases, it is a verb, but it could be a noun also. Okay. But so the fact that this word is in between nouns suggests that this is a verb. Okay. So there are dependencies of the input, but there are very important dependencies on the output that we'd like to exploit. So somehow you can think that this is just a multi-class problem, and if you think like that, you're right, and we're going to do that. Okay. But we want to predict. So there's four or five. There's five multi-class problems. One for each input word. Okay, and so here the multi-class problem is to predict what is the type of this word. Okay, and we'd like to do these multi-class predictions all at once, taking into account the other predictions nearby. Okay, so these are examples of sequence prediction. So another very classic problem within NLP is syntactic parsing. Here we're given a sentence, and we want to predict a tree. Okay, so this is a structure. Trees are well known, well characterized. So while in sequence, you might think that you can, if you have multi-class classifiers, you can solve that problem, and that's a very good intuition. Here it's going to be more tricky. How do you map this problem into a set of multi-class problems? It's going to be difficult because you're not predicting tags, you're predicting a structure. Okay, so how are we going to do that? And obviously, a tree is something that is composed by edges that have a tree constraint. So we might predict each of these individual edges, but somehow there are strong statistical dependencies between these edges of the tree. So we'd like somehow to predict them all at once, making that each and other edge helps each other. Okay, so we'd like to do that. So here's another task, which is far more complicated, which is machine translation. Okay, we have a sentence in Chinese. So this doesn't look like machine translation, because machine translation is like I have a sentence in Chinese, and I want to predict a sentence in English. Okay, But if you look at machine translation literature, there's a whole bunch of methods, and many of them, they don't predict one sequence out of the other. They build some intermediate structure. Okay? So each translation is associated with a structure that explains that translation. For example, in this model, this is a syntactic-based model that in order to do the translation, it builds some sort of syntactic structure of the output. Okay? So the input is a Chinese sentence, and the output is a English sentence with a parse tree with some alignments that say which parts of the English sentence correspond to which parts of the Chinese one. So, in fact, we're going from sequences to these complicated tree structures that encode a translation. Okay, so how do we do that? So outside NLP, there's computer vision, object detection. We're given an image, and we want to predict. We establish a grid. And for each cell in the grid, we want to predict whether what type of object is there. Okay, so this cell here is part of a building, and this cell here is part of a building too. So if you look at an individual cell, it might be difficult, but if you look at all the cells at once, they make a building. So for sure, there are statistical dependencies in there that we want to exploit. So again, we want to do a classification of each of the cells, but all at once. Okay, because that's going to be useful. So that's what we want to do. Okay, so these are a few examples. As I said, the world is full of structured problems. Okay, so today, what I'm going to do, continuing on the two lectures that you had, is introduce the basic concepts for structure prediction. Okay, and to make things easy, I'm just going to focus on sequence prediction, and actually, I will use that simple example of name entity extraction. Okay, because that already it's kind of a very simple problem, but it already highlights what are the difficulties in there, okay? And so, because this is an extension, so what I will try to focus on is to start from scratch, but to try to extend the techniques that we already know, okay? And so basically, so if we have machine learning methods, including theory and actual algorithms, so the basic question is, what can we borrow from standard classification? How can we extend that and hopefully have that the theory still applies, okay? But here we are not just predicting binary. We're not making binary prediction. We are predicting structures. So last Saturday, Noah Smith talked about HMMs, which in fact is a formalism that models sequences. Okay, it models sequences of states that generate sentences. Okay, so this is an HMM is one of a structured formalism. Okay, so if we already have these things, how can you make? I mean, what can we borrow from this, and what's the relation between standard classification and this kind of HMMs and things like that? Okay, so what I'm going to explain today is summarized here, and the main lesson is that, or the outcome, or the current state of the art is that essentially from the theory of machine learning, the paradigms of learning are the same. Okay, so the rules of generalization apply to any sort of machine learning problem, no matter what's the nature of the structure. Okay, but when we look at the algorithms, there's going to be something that needs some thinking. Okay, and this is a computational aspect. Okay, so some of the computations behind learning algorithms are going to be prohibitive, and this is because the fact that we're predicting structures that quickly grow. Okay, so we're gonna have to pay attention and actually introduce some restrictions of what methods and representations we use, such that everything is computationally tractable. Okay, and as a matter of fact, we're not going to reinvent from scratch all those methods, but actually we're going to use this type of representations and algorithms that make things efficient. We're going to take them from HMMs and things like that. Okay, so we'll see that the algorithms that Noah introduced last day, namely Viterbi and forward-backward, are actually of it's a central piece of this method for sequence prediction. Okay, so what I'm going to do today is to is to go over these things and try to make this clear. Okay. So this is the introduction. The first part of this lecture, which is going to go until the break, is going to be on what is sequence prediction and what are the models for sequence prediction. So if you have questions, feel free to ask them as we go, especially if these are clarification questions. Okay, I mean, there's no point in not understanding something. It's much better that if you have a question, so probably most of you have the same question, so it's better to ask. Okay, especially for clarification. Then for more other types of questions, then we can maybe leave them for later. But for clarification, please feel free to interrupt. Okay. So I will start by formalizing a little bit what is sequence prediction. Okay. So in much of the class, I use notation. I use lots of formulas and equations and notation. So my slides are kind of notation heavy, but hopefully it's not that complicated. It's also self-contained. So I have to spend a bit of time introducing that notation. Okay, but hopefully it's not going to be too heavy. Okay, so let's start describing what are the objects. So X, it's going to be a sequence. Okay, an input sequence that has n elements. Okay, so each of the elements could be anything. Let's think for now that they are words. Okay, so we have a space of words X, and then we build sequences out of these words. Okay, but it could be anything. Okay, and the outputs are also sequences that each of the I'm going to call this label. Okay, and so each of the labels belongs to one predefined set. Okay, and we have L labels, but it's one predefined set. This is like in multi-class. Okay, so this will mimic multi-class prediction. The main difference is that instead of just having one of these elements, we have a sequence. Okay, and in this particular instance of sequence prediction I will talk about, I will make the assumption that the output structure is of the same length, namely that there is one output tag for each input tag. Okay, this doesn't need to be the same. There's many problems in which this is not the same. But this, I'm going to focus on this type of problem because it's the most simplest one. Okay. Okay. So we're going to give training data. This is supervised machine learning. So we're going to give pairs of inputs and outputs. Each of these are sequences. Okay. I'm going to have this, and I want to learn a predictor that maps X to Y's, and that works well. Okay. So the first question is to understand what is this predictor, okay? And that's what we're going to focus on until the break, okay? Understand what are functions that take sequences and input and predict sequences of output, okay? So this predictor, so each of the inputs has a certain length, but we want to learn predictors that work for any length, okay? So we work with any sequence, okay? What is fixed here is that the length of the output is equal to the length of the input, but the predictor will work for any length, okay? It accepts any sequence of any length, okay? So the first thing we need to do is to understand what is the output space. So for a very simple example like we saw before on name entity extraction, let's say that the set of output labels, it only has 3 labels, which means, so this is a location word, this is a person word, and this is a word that means that it's not an entity, okay? So let's say that we have an input, Jack London went to Paris. So what is the solution space, okay? The solution space is the set of all output sequences, okay? And this is built by, for each word, we enumerate all the tags, okay? The 3 tags. So there's these 3 possible tags for this word, these 3 possible tags for each word, and so on, okay? And so what is a solution is a path, okay? So this blue path is a labeling of the sentence that says that these 2 things are persons, this is nothing, and this is a location, Okay, this is the blue path. Okay, this is one solution, and the red path is another one. Okay, so for an input sequence of size n, there are y to the n possible outputs. Okay, so if y is 3 and n is 1, 2, 3, 4, 5, so we have 3 to the power of 5 possible output solutions. Okay, because n, which is the length of the input, is in the exponent, we say that this grows exponentially, okay? Which means that we cannot afford enumerating all possible paths, okay? We have to do something that can explore the output space efficiently, okay? And so, to many of you, this will suggest shortest path things or algorithms like that, and that intuition is correct, okay? So we're gonna call this as some sort of shortest path problem, okay? But it's very important to, so structure prediction applies when we have this exponential dependency, okay? So depending on what are the output structures, so that will change. But what it doesn't change is that it's exponential, okay? It will change the number of structures, the shape of them, and the type of algorithms we're gonna have to employ, okay? But it will not change that we need to have some sort of predictor that works on this exponential space, okay? And I'm gonna now work around 3 possible solutions. The first two are, just initial solutions that will have some problem, and afterwards we're gonna identify what is the class of predictors that we want, okay? So the first solution is the one that ignores that these are sequences and just says that these are multi-class problems, okay? So let's start there, okay? So I'm going to call these local classifiers, where by local, I mean that, so at a certain time, I look at just one position, and I ask what is the tag there, okay? At another time, I'm going to look at other parts of the sentence, okay? So I'm going to decompose the output sequence, or the sequential problem, into n independent multi-class classification problems, okay? Because we already have multi-class classifiers at hand, this will be as simple as applying that kind of methods. Okay, I can formalize that in this form. So I fix one position I, and so the output label at position I, yi, is going to be the one that maximizes, so out of all possible labels, out of all the space of labels, the one that maximizes some score, okay? And this score is going to be given by a linear classifier, okay? So what is a linear classifier? Then here I'm recalling what Stefan discussed in his lecture. So a linear classifier is can be formalized as the inner product between a weight vector and a feature vector that represents our assignment, okay? So here the situation is that we have a full sentence X, that's the input, a fixed position I, okay, so it would be 1, 2, okay, I is 2, and a candidate label L, okay, and we iterate over each label, but at each point we have a fixed one, okay? So we're going to have this feature function that takes this and gives us a representation for this assignment, okay? It's a candidate assignment, okay? And W is a weight vector of the same dimensionality of this representation, such that the inner product gives us a score, okay? So the question, how this works is that we supply this feature representation, and then we use machine learning to learn the parameters W, okay? We want to learn, given a certain representation of inputs in a certain position, we want to learn W such that this thing works well, okay? So if we have this classifier, if we have a trained W, how are we going to produce a sequence of outputs? Well, it's very simple, because at each position, we just need to do a classification. So at test time, we predict the best sequence by going over each position, predicting the best label at each position, and just putting them together, okay? It's really very simple, okay? While this is simple, I will now go over describing how we build these feature functions, okay, or how this was built with engineering, okay? And that's going to be useful because we're going to end up extending this to deal with more expressive representations that take into account the sequence, okay? So in order for me to make sure that it is clear this linear relation and the representation, I will have to spend some time describing how we build these feature functions, okay? So this is a bit of an engineering technique, okay? So it's more of a construction rather than something theoretic to understand. But as I said, it's going to be important to be comfortable with that, okay? Such that we can understand what are there's going to be a trade-off between representation and computation, and so we'll not, when we decide how to build a structured prediction, we're going to have to take these issues into account, okay? There's a trade-off, so it's important always to be able to identify how expressive our model is, okay? And to be able to identify how expressive our model is, the best thing is to understand exactly what kind of features, what kind of parameters our model has, okay? So I'm going to do that. So as I said before, so f of xil, okay, is a function that produces a vector of features, okay? So this thing is a vector of d features, so it's a d-dimensional vector, okay? We can plot it like that, so this would be a vector, and this is the coordinate number 1, coordinate number j, coordinate number d, okay? So what is each of these coordinates, okay? So in NLP and many other machine learning things, so when you are given a machine learning course, general one, the feature representation is always given, okay? So you assume that there is a feature description of the inputs, okay? So here, it's the engineering part where we actually don't assume that. Our inputs are sentences and a position, and we actually are going to build one, okay? So that you can see what features we use, okay? So what we do is to have functions that compute for each of the dimensions of the feature vector, they compute the value of the feature, okay? So what's in a feature, what does a feature function does, okay? So let's say, one of the dimensions, and so what's this value, okay? So this is going to be a real value in general. So what is this? Okay, so in general, it's anything, any feature that we can compute using x, the full sentence x, a position y, and a candidate label L, okay? So this is the input, anything we can compute out of that. What is going to matter is to have features that are good indicators of whether this label is good or not for this input, okay? So here, this is describing nothing more than position I of this sequence, and we're trying to assign label L. So we need to describe how good is this assignment, okay? So what is very common in NLP since the early 90s is to use what's called indicator features, okay? So these are binary value features looking at a simple pattern of the input, so x and the position and the actual label, okay? So let me give you a couple of examples, okay? So this, if you haven't seen this, it might sound a bit kind of strange, okay? But I hope to make sense out of that, okay? So a feature might look at whether the current word is London and the label we are attempting to assign is location, okay? So it's just looking at an assignment, okay? And it's saying one, whether the pattern associated to this applies, okay? So if this pattern applies, it says 1, and otherwise it says 0, okay? So that's one feature. And another feature might look whether the next word, xi plus 1, is went, and L is a and the label is location, okay? Note here that we're representing position I, label L with position I, but we're looking at the next word, okay? So we're describing the ith position by looking at the next word. This is given, so we can do that, okay? So in general, we can write anything we can compute using the full sequence, a position, and the candidate label, okay? So how do we actually, so it seems, So this thing we build it by, we're giving it to the learner, okay? So it seems like impossible that if I want to build an name entity extraction, I need to write these things which are at a very fine level, okay? I'm not gonna do that. So what we do in practice is to have methods that generate a huge amount of these things, okay? Of course, automatically, okay? So what we use is the notion of feature template. So feature template is nothing more than what I just described. Is a method that generates indicator features in a mechanical way, okay? And in such a way that with a very simple description language, you can describe the data in quite rich ways, okay? So it works just like that. It's just a construction, okay? And it's rather simple, but it's just a construction, okay? So a feature template is identified by a certain type and a number of values, okay? So for example, if I want to mimic this feature thing here, what I'm gonna do is to say, this is the extraction of a word, and it takes a certain label A and a certain word W, okay? So this specifies the function, okay? And it's a function that applies to this input, okay? And this function says 1 if the current word is W, this W is the 1 of the template, and the current label is A, okay? So, which means that if I instantiate, so the identification of this dimension is identified by the tuple type, a certain label, and a certain word. So if I instantiate this with different labels in my label space and different words in my vocabulary, I'm going to get lots of features, okay? So for example, if I say that A is location and W is London, I have that the dimension associated to this extract whether the current word is London and the current label is location, okay? But if I change the type, the label, I get the same feature extraction but with another label, okay? And if I change the word, I get another one. So for each word, so London, I can try London with every possible label, and Paris with every possible label, and John with every possible label, and the with every possible label, and so on. So with just this feature template, I have features that look at every possible word and every possible label, okay? Have all the combinations, okay? And of course, I can write lots of feature templates, which I'm gonna show in the next slide, okay? So when we use feature-based models, we don't write actual feature dimensions, okay? What we do is we write feature templates like this manually, and then we go to the data, and then we look at what are the words in our data, and we also look at what are the tags in our data, and so we instantiate the template with every word and every tag, okay? And that generates one feature for every possible set of these values that identify the tuple, okay? So because there are lots of words, so in a data set there's, I don't know, tens of thousands of words, okay, in a vocabulary. So just this simple template will generate, let's say we have 100,000 words, and we have 3 types. So this feature template already generates 300,000 types, 100 dimensions, okay? So this generates a very high dimensional feature space that is also very, very sparse in the sense that these are just binary indicators, okay? These are just, so this feature template generates 300 dimensional vector that is super sparse. It's only zeros and ones, and in practice, a certain input only has a few ones, okay? So this is how we construct a feature space, okay, for representing a certain position in a sentence and the label, okay? And then recall that this goes in the context of a linear model, okay? So for each of these feature templates, we have one parameter in our weight vector indexed by the same thing, okay? So what we do is generate this huge amount of features, and then the trick, and that's an important point, we let the learning algorithm choose the relevant ones, okay? So maybe when I introduced this, it seemed like I had to, ahead of time, choose which features would be relevant for my classification, but I do nothing like that. What I do is I take all the words and all the tags, and I let the learning algorithm choose which ones are relevant. Okay, the learning algorithm can set everything to 0 except ones. Okay, so I will let the learning algorithm choose which features are relevant for my task. So let me highlight you how powerful this engineering trick is. Okay, and that's so if you look at any name entity system, at least, well, now neural models, as you might know, are very popular. Neural models do this feature extraction automatically, okay? But if you look at non-neural model for name entity extraction, you'll see that the methods that obtain the best results in current evaluations use this kind of features, okay? So what they do is that we take the input and a certain position, and we extract, we think of certain patterns, okay? The current word, xi, as we saw, we can take features whether is the current word capitalized, does the current word have digits? We can take prefixes and suffixes of our word. We can ask whether our current word is a known location or person, so this is kind of adding knowledge that we might have. So anything you can think about that might be relevant for this task, you can add it here. If it's relevant, chances are that it will improve your method. If it's not relevant, it's not that of a matter, because here you are not deciding how is the prediction rule. Here you are just saying what is the representation, and you're hoping that the learning algorithm will choose which ones are relevant. Okay, so if there's irrelevant, and that's something that we observe pretty well. If there are irrelevant features, the learning algorithms tend to be robust to that. Okay, so it's not a problem if you add too many features. Okay, then it might be a problem for the size of the model, but not for the performance grid. Okay, so we can have templates that look at the current word. We can have templates that look at the context. What is the next word? What is the previous word? And so on and so on. Okay. So each of these templates that look at the word and the nearby input context is conjoined with the output labels, okay? And this is bringing a huge amount of features that represents the input and the output together, okay? So what is the limitation of this in the context of a structured prediction? Who might have an idea of that? So here I gave a method to kind of represent this thing, okay? To represent a certain sequence, a certain position, and the label. And this is kind of very powerful at describing this. But there's one important fact that this thing cannot capture. Yeah, so here. Okay, that's a good question. So it's analogous to what we did here. Okay, so this is the template. Okay, so it's analogous to this. Okay, instead of having one dimension that is the word, we have one dimension for each word. And then to identify the word, we put a 1 into the dimension corresponding to that word. So if you have 10 words in your vocabulary, you're going to have 10 binary dimensions. And then the corresponding dimension is set to 1. Okay, so it's called sometimes one-hot encoding now. So if we so let's say we have 10 words. If we want to represent the current word, we would have 10 binary dimensions, 1 for each word. If we want to represent the next word, we have a separate set of 10 dimensions that represent which is the next word. If we want to represent the previous word, we have a separate set of 10 dimensions. Okay, so this is a very good question to understand the shape of this feature space. Okay, so if we have 10 words and we extract the current word, the next word, and the previous word, we have 3 times, as many dimensions as 3 times the number of words. But this is not all, okay? Because this is representing x and I. So if we also want to represent the output, which is essential, because we're trying to build a relation between inputs and outputs, okay? We need to represent both. So all these dimensions that represent the current, the next, and the previous word are with a product with a label, okay? So it's going to be all of these variable labels. So it's a huge feature space, okay? And this is like huge, very sparse feature space. And if you look, I'm not going to cover that today, but if you look at the literature of plain, this is nothing to do with structure prediction, okay? You will see that there's a need for making representations more compact, okay, to generalize, okay? And word embeddings and things like that are related to this, okay? But what is, so this is just plain classification, okay? I'm just describing a way to predict a certain tag. So what is that I'm not capturing here?
Namely, it can be several words.
Yeah.
Like, for example, in Jack London,
Yeah.
we know for sure that Jack stands for a name.
Yeah.
You can kind of guess that the second word is part of the name. And
Yeah. So that's the point, okay? So there are interactions in the sequence, okay? We know that this is, so at the previous step, we're going to also classify that this is a person. So we might capture, so the fact that London is a person is because it's following Jack, okay? So we might actually capture that this is a person and not a location because we are capturing the previous word. So we can say if the previous word is a first name, that might be a location, a person, okay? We might establish a dimension that relates this word to this tag, okay? But it's a lot easier if we can do this, okay? If we can take advantage of the fact that we're also predicting the previous thing, okay? And we'd like to have a feature that says person labels tend to follow person labels, and that's very strong, okay? Because no matter what's the input, if you just see persons and there's input evidence that the word below is a person name, so you just keep doing that, okay? So features cannot capture interactions between labels. Why not? Well, because I kind of constructed a feature space, and because of the assumption I made at the beginning, my feature extraction, which is kind of, it seemed like very general, but actually it's only taking the input, a position, and a label. It's not taking two labels, it's only taking one. So I cannot extract the previous label because I don't have it here, okay? And in order to, if I want to have it here, I need kind of to change, okay? I cannot reduce, yeah.
So basically you are saying that we can join several different models that have one label, and basically you can make like this is a multi-label model or single-label model.
It's not multi-label. Multi-label is when at a certain position you have several true labels. It's like that here there are several positions, and I want one classifier that predicts the label for each of them, but I want to take interactions. So I want to have parameters. So in this construction, I don't have parameters that look at two labels at once. And I will need to modify this such that this is the case, okay? Okay, so this was a recap of feature-based classification, okay? There's nothing about structure prediction. For structure prediction, we'd like to have this thing, okay? So let's change paradigms. And let's go to HMMs, okay? That's Saturday's lecture. And if we look at, if we recall what are an HMM, actually, an HMM is actually a sequence model, so we could try to fit name entity extraction as an HMM distribution, okay? So in that case, we would set that the states of the HMM are these name entity tags, and that this thing generates a sentence. So if you look at the definition of an HMM is like a stochastic model, it's like a machine, okay, that generates sequences like that. So it has a probability for starting with a certain label. What's the probability to start a sentence with a person name or with a location name or with a nothing label, okay? And then, interestingly, it has these transition parameters, which are what's the probability of moving from person to person, and then from moving from person to nothing, and from nothing to nothing, and from nothing to location. And that's what we want, okay? We want what's the probability of generating another person word if I have generated the person word. That's exactly what I want, okay? So that's good, okay? I want parameters like that take two adjacent output labels and have a weight for that, so that they can say, so that I can capture how likely it is to go from one label to another, okay? So that's good. But then an HMM has these two parameters and has a third set of parameters that, given a label, generates a word. Okay, what's the distribution of words under this label? Okay, and that's okay. I have all the, so I have the expression of so an HMM computes this distribution, probabilities of inputs and outputs, sequences as a product of these parameters. And I can do, that's okay. I can learn that. I can do predictions using the Viterbi that, given the sentence, compute what is the most likely sequence of tags. That's precisely what I want. Okay, given a sentence, give me the output sequence or the sequence of states in the HMM terminology. But there is a problem here that I hope I had convinced you that it was kind of very handy to have this, even if it's manual, it's very handy to have these mechanisms for doing feature extraction, okay? Because we can have features that just encode the context of words. We can have features that encode previous knowledge about what are first names. So we have in the previous approach, we had full expressivity for adding those features. And here we don't, okay? We only have these three sets of parameters. And how can I capture that my word is capitalized? So for English and many other languages, this is a clear indication that it's a name entity thing. So how can I, in an HMM, the relation between labels and words, it's only described by this table. This is a table of parameters, okay? That there is a weight for each word and each label, there is a weight, okay? We'd like to go finer level, okay? So to capture whether there's capitalization digits, prefixes and suffixes, okay? That can give you lots of information. Even next word and previous word, I don't have parameters that look at this directly. The HMM can do inferences like that, but it's not clear that I can reinforce this connection by the fact that I have a verb here, okay? So it's not clear how to capture these things. And why is this? It's because an HMM is something that is a stochastic model that it's defined. When it was defined as a language model. It was defined as something, a device made to generate sentences, okay? And compute probability distributions of sentences. And here, okay, so in order to do that efficiently, there are so there is the independent assumption that given a label, the token below it is independent of anything else, okay? Given this, there's a distribution of tokens. So actually, it's designed such that the word below here is independent of anything else except given this person. So in fact, it's designed such that there's no direct dependence between this word and this word that via this, okay? There's no direct dependence. So this is by design, okay? And this was made because the original purpose of HMMs was to describe sentences. And here we're inverting the goal, okay? We're given a sentence and we want to get the sequence of states, okay? So this doesn't match well with having very expressive features, okay? So to recap, so far you've seen two sets of techniques. One is just linear classification, okay? So how we would approach sequence prediction is by having independent predictions for each position. The main advantage is that this is very feature rich, okay? We can write down. So this is a black box where we supply the templates. And while this might sound tedious, this is actually very handy because we can put anything we want with the advantage that machine learning today is very robust to features. So it doesn't really matter if we put too many features. Actually, it's a good approach to put lots of features with some intuition and let the algorithm capture what are the relevant ones, okay? So this is good for feature reach. But the way we did it, we cannot capture label interactions, okay? And the other side, it's like a solid stochastic model. It is structured by itself, okay? It takes into account interactions between labels. That is what we would like to have here. But then there's no fine-grained features. We lose these, okay? So what we want, obviously, is to have both things, to have something that is both things at the same time, which is what precisely I'm gonna look at, okay? So the approach 3, which is the model I'm gonna discuss, okay, and it's the basis of structured prediction, is this kind of thing. So we're gonna start from scratch, okay, and say what we want, okay? So I want a single classifier, let's say, function that maps sequences, input sequences to output ones, and I'm gonna start with like the classification approach, okay? But instead of breaking it down, I'm just gonna say, okay, in general, I want to represent input and output sequences all together. And I want to have a linear prediction, okay? So it's like a classifier that takes full inputs and outputs at once, okay? So if I define a classifier like that, this will be the prediction, okay? I'm gonna loop over all possible sequences and choose the one that is the best, okay? I'm mimicking classifiers, but at the sequence level, okay? So we're gonna solve this, but there's two problems that need attention, okay? And they are related. So the first is that we're gonna have to revisit how is the feature function such that we can encode full sequences, okay? It will not, I mean, a priori it's not clear how to encode. Recall that our sequences are of arbitrary length. So when we have classification, we have a fixed thing and one label, okay? So we saw how to represent that. We're gonna have to engineer or think about how can we represent things that are of arbitrary length, because this inner product space is of fixed dimensionality, okay? So we need to take two pairs of sequences which are of arbitrary length and put them into some space of fixed dimensions, okay? Which will define our linear prediction. And the second aspect, which is important, is that the number of candidates is exponential, as I said at the beginning, okay? With respect to the length of our sequence, there are going to be exponentially many. So this search for the best sequence, we cannot do it by brute force. We cannot go over every sequence, okay? So the solution will be combined, okay? The way to make this tractable is to make this feature representation in a way that will allow to solve this RMAC problem efficiently. Okay? I'm telling you what's going to happen, but so now we're going to look at this, okay? Any question of the setting? Yep. It doesn't. It doesn't have to, but today we're going to look at linear structure prediction. But it doesn't have to. Okay, we're extending linear prediction to the structure case. Okay, you could take nonlinear prediction and go to the structure case. But if you do that, so having more complex functions for learning mapping will not get you over this fact. Okay, so that's the point. That's why we start here. Okay, and actually I want to make this point clear. So linear models so all this framework was developed the last decade, and it borrows a lot from stuff that goes decades and decades ago, like HMMs. And today, it seems today that linear models are kind of saturated, and everyone is doing nonlinear methods and neural networks. Okay, and that's the direction to go. But in order to do that, these concepts are still there. Okay, so you cannot. It's not that neural networks solve you this. I mean, this will always be something fundamental of this. Okay, so you need to have methods that can do the search quickly, okay, or efficiently. Okay, so I will discuss a little bit more. Okay, and you'll see. I think that in 2 days you're going to see, or in 3 days you're going to see nonlinear models for this. Okay, which give up the nonlinear models because they are not. They give up on doing this exactly. Okay, but So we focus on that because it's fundamental, okay? Any other question? Yeah.
Yes, the definition of the output space, the feature function, is the same for all levels.
What is level?
Why?
Ah, yes, it's the same, yeah.
Yeah, and for example, if you don't need the feature capitalization for one type of label, you could reduce the size of the feature space.
So the model uses a certain representation of input and output pairs, okay? And it's the same representation for all the output pairs. So maybe for a certain output, that type of features are not so relevant to describe that one. Well, in that case, the model should figure out, you should have other ways to represent that. So underlying the model, the representation is fixed. So a model works on a certain representation that we decide ahead of time. So, I mean, if we understood that, we could think that this is not a true problem. I mean, the model should be able. So this is given. We fix this, and we want to learn this. Okay, so we need to understand how do we represent input-output pairs in the case that they are sequence. Okay, we kind of understood now how we build this in the case where the y is a single value, and now I want to focus on the case where y is a sequence, not just one value. Okay. Okay, so it's not going to be rocket science. I mean, there's no super trick. Okay. So how do we represent entire sequence in a fixed vector space? Okay. Okay, so the first thing we're going to think about is what do we want to represent? Okay, of the output, what do we want? So we could look at each of the tags individually, each of the things individually, but that's okay. Look at every individual assignment at once. Okay, but that's what we just did. Okay, so if we do that, we're like classifiers. I'm not telling you still how I build this function, okay? But I'm just telling you what we want to look at, okay? So if we would look at one label at a time, we already did that, okay? So what we can do is, okay, let's look at two labels at a time, adjacent. That's what I call it bigram because it means that they are adjacent labels, okay? So we look at person, person, and then person. So any adjacent label, yi minus 1, yi, is a label bigram. So we could define a feature function that somehow has the expressivity to look at every bigram in the output sequence, okay? And y sub too, okay? We could look at every trigram. We could look at every chunk of size 3, okay? And y sub there. So we could look at every chunk of size n for a fixed n, okay? This n, okay? So a fixed thing. Or then we could look at the full one, okay? So if our feature function looks at chunks of the output that are fixed size, we're gonna see this is gonna be, we will call this a factored representation, and it's the search problem is gonna be tractable, okay? If we want to look at the full label sequence, even if we don't know how to exactly do that, this would lead to an intractable problem, okay? So we're not gonna look at this. We're going to look at methods that represent input-output sequence pairs by looking at each. I'm going to focus on bigrams because it's the simplest one, okay? By looking at every bigram of the output, okay? So again, you will see with neural networks and nonlinear models, you'll see how to do that, okay? But today, we're going to look at this. Okay, so I'm going to call this a factored representation, okay? A factored representation in this form will lead to a tractable model. So I'm going to now extend what we saw. Okay, this is hopefully a bit simple. Okay, so now I redefine my feature templates. Says that instead of taking one label, they take two. Okay, this might sound a bit tricky. I have a position, and I have two labels which sit on top of this. Okay, so I choose the label on top and the previous one. So this kind of arbitrary, I fix it like that, okay? I could look at the next label, I could look at different things, but What is important is that they are adjacent, okay? Whether, with respect to this position, it's not important. It's not immediate to see that, but it's not gonna be important, okay? So just, let's work with this construction. Okay, so I have a feature template which is analogous to the other one, except that now, instead of using one label, I can use two, okay? So it's gonna be clear that with this expressivity, I'm gonna be able to have features that say, if my current word is London, I'm gonna, and my two labels that sit on top of this with an offset are person, so okay, this template could be instantiated like that, okay? This template, if I give value to A and B to be person, and to the word to be London, now I capture that I have person, London. And here I capture that I have, here I'm evaluating the template at position 2, so I have person, London, and the same template, the same feature, I'm evaluating it at position 3, okay? So here I don't have person, London. I have person, nothing, went, okay? So this feature template evaluates to 0. And this, at position 3, I evaluate person, nothing, went. Person, nothing, went. So this says 1, okay? So here I'm capturing the fact, this template here is capturing the fact that whenever you have went at position 3, and so the previous label is person, okay? It's capturing this thing here, okay? So I have this expressivity of capturing two things and some context of the input, okay? So this is now super expressive. My illustration here, it needs to be understood what I mean by this. So recall that I'm defining a function that can represent any input and any output, okay? So here I have two inputs, X and X prime. They are independent inputs. Jack London went to Paris and my trip to London, blah, blah, blah. And I have three outputs, okay? This thing and this thing and this thing. And my function can represent any pair. This with this, 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 with this. So I'm highlighting here how a certain feature template extracts patterns, okay? So this one extracts that a bigram of persons and London, okay? So this thing, if the word is London and I have two persons, so it fires here, okay? And this one extracts that I have person, location, and London. So it fires for this output sequence and this one. And this one looks at the preposition. It takes the fact that I have two Paris and location, okay, or two London and location. So different, a feature template will capture parts of the input and parts of the output. So what we want is to have this. So that's why we call this factored, okay, because it captures features of the factors, of chunks of the input of the output, okay. So this gives us a super expressive thing, okay, that can capture, as I said, parts of the input and parts of the output. Okay, so I described you how to extract certain things of a certain position and two labels, okay? So this thing gives me a d-dimensional feature vector for a label bigram at a certain position. So its dimension is typically a Boolean, okay? Now, what I want is this, a feature function that represents a sequence with a sequence. So I'm obtaining this by summing these over positions, okay? So because these things have a certain length, and this depends on a position, I'm taking, for every position in this pair, I'm summing these feature vectors of each position, okay? So what does it mean? It means that, first, it means that they live in the same vector space. Okay, it means that this feature space and this feature space is the same, except that here I extract indicators, and here I count how many indicators I have. Okay, so. Right, so what we provide are feature templates that extract things at a certain position, and my representation is going to be a sum that aggregates these patterns over the length. Okay. Yep.
How do you handle y0? Because you start with 1 and
Yeah, okay. So y0, so sometimes, okay, sometimes we just put like a special label to define this, okay? But yeah, this is not to not overcomplicate the notation, but it's true. So for the first position, this is undefined, okay? But we just give a special value, okay? So this might not sound very intuitive. Why am I summing? So I'm just forgetting, so I'm capturing things so what this means is that I'm capturing things at certain positions, and then I'm summing, so I'm forgetting where they are, okay? So if we put it back together, this is end of the definitions, okay? So we're gonna put it back together, okay? And we're gonna have a linear prediction like that, where I defined the representation of input-output sequence pairs as the sum of feature vectors that are evaluated at each of the positions, okay? I sum over positions, and then I get my thing, okay? So one remark to do here is that this is a linear model, okay? So in general, what is a linear model in general, okay? So this inner product here gives us a score, okay? So linear means that, recall that this is fixed, this is given by us, okay? So linear means that the score we predict is linear with the parameters, okay? If we change one parameter, the score will change proportionally, okay? So because this is linear and f is a sum over positions, we can take this and write f as a sum, and we can actually put the weight vector inside, okay? Which means that our score function, we can think that there's two views of it, and this is important, okay? There's two views. There's like the classifier view, like you give me a representation of your input, and I have a linear prediction, okay? So we stay in this thing. We don't care how our feature representation is made. It's a linear method, okay? Or there's the other view that says, my prediction is so this is also a linear prediction, okay? But this is a linear prediction that it's a classifier of bigram labels at a certain position, okay? So this means that actually I have a classifier that goes to each position and predicts what is the best bigram label, okay? And then if I want to score a sequence, I just sum these predictions, okay? And it turns out that it's the same thing, okay? It's the same to first describe each position in bigram, aggregate, and do the inner product. Then this is the same than going to a certain position, describe it, do the inner product, and then sum the predictions over the sequence. It's the same, okay? As we can see this, okay? So this is why we call it linear factored, okay? Because it's a linear model, but it's factored one. The fact that it's factored allows it to be linear, okay? So this is what the form of the prediction is, and there are two questions. The first is, okay, but you told me all that, but we still have an exponentially many possible solutions, okay? So for this to make sense, for this to be tractable to compute, you need to show me how, given an input, you select what is the best sequence, okay? So how do we solve the RMAC problem in the presence of exponentially many possible solutions, okay? So that we're gonna see now. And the basic question, the machine learning question is, if you give me a certain representation and you give me data, how do I learn W, okay? So how do I set values to W? This is a learning problem, which we're gonna see in the second part, okay? So any question of the form of the model? So it's the same question as before. We like it to be like that. So There are certain cases. So there's two cases. So the fact, the fact that I don't want to, the fact that it's a factor model. So let me. So a factor model is one that, to predict a score of an output sequence, sums the scores of parts of the sequence. So that's a factor model. So if this model, if for a factor model, the argmax problem will be solvable. Then how you produce those scores could be in a linear relation like this one, or in a nonlinear one. So the fact that it's a linear relation allows us to go here. So if the relation of the score of a part was not linear with respect to representation, I couldn't do this. Because I couldn't get the W out of the sum. I couldn't do this. So I can go from here to here because it's linear. So the fact that it's linear helps us connect with the theory of machine learning, of linear prediction, margins, lots of stuff. And convex, and importantly, for optimization. So the optimization problems will be convex. So we don't have to guess, or we don't have to hope that that we will not screw. Sure, I mean, it is possible. People do it all the time today, but then you lose properties. So, and there's a huge question. I mean, most difficult problems have some hardness, some MP hardness. So it's like, what do? You make your model simple but tractable, or you make your model not tractable but more realistic. Welcome to computer science. I don't know. But in order to start, so what is necessary is to understand what's the boundary. But you'll see a lot of neural models that are factored. So they exploit these things. All right. Hopefully now we're going to start using instead of producing. So we're going to start using things that more or less we know. So let's focus on the prediction. So now this is a prediction. It means that the W is fixed, and actually we're given an input. So the input is also fixed. We don't care about that. So what we want is to solve this problem. We want to find the Y that maximizes this score. And that's the solution. So we can do this because it's a factored model. We can do this with the Viterbi, which takes time, can find the exact solution, namely the sequence that really gets to is the optimum, the maximum one, in linear time with respect to the length of sequence, and in quadratic time with respect to the number of labels. So the number 2, the exponent 2 here has to do with the fact that there's two things here. If we wanted to have 3 tags at a time, this would be a 3, and 4, it would be a 4, That's why if we want to have unrestricted, then there's going to be some k or n, and it's going to be exponential, so not tractable, So the tractability of this depends on this exponent, which is the number of things we look at once, Let's just I'm not gonna, I'm gonna a little bit present the intuition of Viterbi, but just a little bit, because everything is fixed, I'm gonna change the notation, and I'm gonna call. So because so now I look it like that. I look that, you see, I prefer this form here, not this form here, because this form here gives me more the sequential thing. This doesn't tell me that these are sequences. This tells me that this is a sequence, and I sum scores over time. So what I want to do first is forget that we have linear models, and say that for each position and every bigram, AB stands for a label bigram, I have a score, such that I can write this like that. I should have written this with this. It's here, So I'm solving this problem. So effectively, connecting with your question, So these scores at every bigram position could be given by anything. Okay, so the Viterbi algorithm applies whenever you want to solve this problem. I don't care where these things come from. Okay, so why Viterbi works? Well, because so one sequence has all these scores and we sum. Okay, so the intuition is that the output sequence that share bigrams also share scores. So let's say that this illustration it tends to be a sequence. Okay, so this is the position 1 and this is the position n, and this would so this thing is like a partial sequence from position 1 to position I minus 1, and this is another possible sequence, and is another possible one. Okay, so if I have this sequence, let's say that this is a sequence that goes up to I minus 1. Okay, I have all these different ways to complete it. Exponentially many ways to complete it with respect to that length. Okay, but all those ones, let's say that they share this prefix. Okay, so the score of any of these shares the initial scores. Okay, all the labeled bigrams here have their own score, and so no matter how I finish that, the initial part will not change the score. Okay, so this allows to open the dynamic programming toolbox and say that define subproblems such that, you know, the optimum of the problem, the full optimal, okay, can be written as smaller optimums. Okay, and so it's by dynamic programming. So meaning that, so for example, if someone gives me the best subsequence up to this position ending with each tag, and the best subsequence from the end to here up to this tag, okay, I have 3 tags, and I'm kind of going forward and backward, and someone comes and gives me these 6 subsequences. Okay, I know that the optimal one is one combination of, so there's 9 combinations here, this with these 3, or this with these 3. So the best one needs to be one of these 9. Okay, and what's the difference? So how do I connect this subsequence with this one? I just have the score. I just have this score for position I, y minus 1 is location, and yi is person. Okay, so I can do that. Okay, so how it works? Is right. So how it works is actually in the forward pass. Okay, so I define a dynamic program that computes the best subsequence from the beginning to a certain position, each time keeping the last tag. Okay, so we have 3 tags. I always have to keep track of 3 best subsequence up to there. Okay, and if I want to extend it, okay, I want to compute what's the best sequence that ends at this point with tag location. Okay, I know that it's one of these. Okay, so at each extension, I only need to compute as many scores as the number of tags. Okay, and I keep doing that. Okay, so you keep doing that forward, 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 and then you get the best one. So this is the dynamic program. This is a bunch of equations that are recursive. Okay. And that they solve, so in the context of our model, they solve this. Okay, so this is the recursive, this is the dynamic problem that depends on a certain position and a certain tag. Okay, so, well, I really recommend, so Viterbi is really important. So so some of you might already know, and even, so you really know Viterbi when you play with it. You can program it, you can solve it by hand several times. You can try to, so there's all these extensions of these methods. There's the naive implementations that then when you run them take a huge amount of time, and ones that take advantage of certain sparsity patterns or certain things. So I recommend, so if you want to know about this, you have to work on it. So that's why I'm not presenting it more than that, because what is important is to know the existence of this and what does it solve. And then if you want to understand the mechanics of the algorithm, you have to work it out. Okay, so here's Viterbi. So to recap, in the first part of this lecture, so we want to predict output sequences of, okay, and we have seen that if we want to, so if first, if we want to make, if we want to have descriptions of the output, kind of in a feature extraction way, we need to kind of represent, so to write features, it's a kind of handy to look at just parts of the output, because have features of the full output, it would be difficult to me to just have a features of the full output. So it's kind of handy to break down a sequence into chunks and then represent features of the chunk, okay, combined with the input. What is very important is that we combine things of the output and things of the input, because we're trying to decide what's a good assignment of inputs to outputs, okay? So our feature needs to look at the assignments, okay? And instead of looking at full sequences, we break it down into chunks in the way we said, and then we say, okay, let's define a linear model on top of that representation. This is flexible. This is arbitrary features, and there's only one horizon, which is this order of the factorization, okay? That's what makes it tractable, and that's what defines the cost of predicting. Actually, you can, as a recap, you can think that would be here, yeah. It would be here. So if we actually take one tag only, okay, not that this goes, not that just plain classification is just a specific case, okay? So if we look at one tag at a time, then this exponent is 1, and we can solve it very trivially, okay? It's just, there's no dependence on the other one. So it's actually a natural extension of classifiers that look at 2 tags at a time, okay? So next we're gonna look at how to learn W. And I'm gonna just look at probabilistic log linear models. This gives, so conditional random fields, which is super popular, is this, okay? Is using a log, I will show that. And also what is very popular and handy is to think. So there's 2 ways of think, there's 2 common ways to think. One is the probabilistic one, and one is the margin-based one, SVMs and things like that, okay? So it's the extensions to that, okay? So before the break, what is learning, okay? So this is a little example, okay, that kind of try to highlight what we're doing. Let me see if I can explain that. Okay, so here's my training data, okay? Obviously, it's a toy, okay? So I have 6 training pairs, okay? It's this name entity extraction problem. So Maria is beautiful, this is a person, and this is nothing, nothing. So note that these are also to be predicted, okay? So everything needs to be, all the tags need to be predicted in general, okay? Even though for an application, then we would only pick the entities, but the machine learning problem is to predict the full set of things, okay? And so we have these things, okay? And now we have the freedom to design feature templates. Okay, so let's say that, okay, this is prepared with a set of templates that are the common ones, okay? And so the learner, okay, once all this is given, the learner needs to set the weights such that the correct sequence is the one that is the maximum, okay? So initially, all the weights are 0. Let's say all the weights are 0. So what's the score of any sequence? What's the score of this sequence? 0. Yeah, it's 0, because there's all the weights are 0, okay? So what we need to do is to set up weights which are associated to a certain instantiation of the template such that the good ones get on top, okay? So now we're even, okay? So I'll start with the first, okay? So what's most prominent here? What's the simplest way to, let's think the multi-class way, okay? Let's not think sequence prediction, but our goal is to make the sequence correct, but it's obvious to think multi-class, okay? So what is obvious is that most, and of course this is prepared, but note that the lowercase words are always this dash tag, okay? So we can have a weight that says anything that is lowercase and has this tag receives a weight of 1, okay? So so now what is the score of this assignment? It's 2. Why? Because this pattern is observed 2 cases, okay? But still, what is the score of location dash dash? It's 2. And what is the score of dash dash dash? It's 2 or 3? 3 or 2? Why? Yeah, so it's not 3. Why? Because it has to be lowercase. So if it's uppercase, you don't gain any point, okay? So this gives a point for lowercase words which get this tag, okay? Okay, so we have that the non-entity tags kind of solved, but now we need to deal with the ones, okay? We need to make the correct sequence the best one. So, okay, let's say, okay, now we need to deal with the uppercase words, which is the difficult part. So we could say that the uppercase, so anything that is uppercase is person. Okay, so we get all these things right. Okay, what do you think? There's a lot of errors here, right? So is that a good thing to do or not? Huh? No? Do you have a better suggestion? So first, one thing that we see is that, so I think that the blue here are the correct individual assignments and the red ones are the incorrect ones. So how can we quickly make this better? Huh? Start of the sequence would be 1, but let me just say that, so having things that don't work perfectly is okay. But if you use those things, you use the best one, okay? So most uppercase words, so if something is uppercase, what's the most likely class? It's not person is in this example, of course, it's location, okay? So, okay, let's use simple features, but let's use them more cleverly, okay? So we get a slightly better score with this, okay? And, okay, it's time of the break, so we can do this with simple features, and we could use the start of the sequence and all that. We can lexicalize. So we can, let me finish this. It's going to take 1 minute, okay? So we can say, well, if the word is Maria, make it person, okay? So, so with respect to this rule, we make additional rules. So, but to make this, we have to have we have to untie it, okay? We have to. So we made a mistake here of a score 1, and to correct this, we have to have better weight for person, okay? And so we could be doing all this, okay? And we could use that the next word, if the next word is went, use a person, okay? So it's capturing this. So note that if I have the template next word and current tag, I might not even know what are verbs of movement, okay? But the data, the learning data, by training this, I might actually induce that this word indicates person names. I don't need previous knowledge that this is a verb that takes things that move as an object to just guess that this might be person, okay? The data tells me that, okay? Because this pattern makes this example correct, okay? So I might actually, you can call this learning if you want, okay? You can learn that this word indicates that the word behind might be a person, okay? So that's what we gain by using these huge mechanically built feature spaces, and we let the learning algorithm figure out what is the good set of weights to do that, okay? So same thing for playing and so on. I mean, there's all these things you can do. Here, none of these templates is using actually bigrams, okay? But I could do this, okay? If it's person and the two words are in uppercase, okay, so uppercase, so words, contiguous words in uppercase should have the same tag, okay? And I can also use negatives. I can say, if the next word is played, don't use location, okay? So because Argentina played, Argentina normally is a location, but if it's followed by played, use it as an organization because it's kind of, this doesn't mean the country, this means the people of the country or the football team, okay? It's an organization, okay? So I can use negative, okay? So overall, I can write templates and make all these work, okay? So next part, we're gonna see how to automatically do this. Okay, thanks. Yeah, so one, let me take this slide. So one question that came, I think that's important, is like, so this is the position. This is the feature extraction on a template, and this is the position, right? So to which extent the position is part, I can't remember what was the question. So, what's the deal with this position, right? So normally, okay, that is really task dependent, okay, what we do with this position. But first of all, so here, this representation is not positional. This representation is not positional because we are aggregating over positions. So normally the features, they don't use the position. They don't use, okay? But I mean, the computation instantiates, and the computation computes the score at every position. So we use the position, but at the end, the positions are aggregated, are summed over, okay? So then, depending on the task, we can choose or not to make use of the positions. So in the problems we discussed, there was when I was doing this game of the features, there was a suggestion to say, well, if it's the first word, it might be capitalized but not be an entity, right? There was a suggestion here. So it's true, in that case, we can capture, so the first word, to capture that, we use the position, okay? So we can say, is the position the first or the last one, okay? And we can ask these questions. What we typically don't do is to have feature templates that say, Germany appears in position 4. Because that will depend on the sentence, right? So for this particular set of features, it doesn't, okay? So that's task dependent, okay? But the model works with aggregated position. So the use of the position in the feature space, sometimes it's useful, sometimes it's not. In other types of problems, we use relative positions, okay? I think that for parsing, you're gonna see that. I'm not gonna comment on that. Then another set of problems is like, oh, I'm working on a problem that has a slightly different form. Great. These things apply, but as I said before, today I'm focusing on sequence prediction, okay? So if you want to have a factored approach, what is important is that your factorization has some sort of algorithm that can compute this, okay? So if you can do these exact computations under some factorization, then this framework works well, and you can extend it to your problem. And sometimes we have a certain specific types of output structures, and then actually we have to design the actual Viterbi algorithm or extend it to that setting. That's a good set. That's a skill that we acquire when we see several instantiations of these, okay? So first of all, this is not for name entity. Second of all, this is not even for sequence prediction. This extends, as long as your factorization has a tractable algorithm, this works, okay? And then the last question is, well, but now I'm using RNNs and things like that, okay? So what's the difference? Okay, RNNs, they do computations like LSTM, okay? That's an example. So at a certain position, they compute a score of predicting this or that, okay? That score depends from the very beginning, okay? So clearly that's not factored, okay? And then, so then if that works well, why is this useful? Well, I don't know. I mean, this is, whenever this factored, okay, first of all, so just plain computer science, there's all these problems for which the greedy algorithm is optimal, right? So greedy sometimes is optimal. In which cases greedy is optimal? Well, when the greedy local decision So when the optimal solution can be decomposed as a number of greedy steps, okay? So in that case, so greedy doesn't mean suboptimal, but sometimes greedy, so if greedy is perfect, then you don't need that. So if we predict the first tag of the sequence, and then we predict the second one based on the first, and then we predict the third one based on the first, and we never do any mistake, then it's clear that the sequence we predict we're going to be the best one, okay? So it's all a matter of if a greedy approach that predicts the next tag, the next label, given the previous predictions, is always perfect, then, well, first of all, you're clearly dealing with a very easy problem, okay? So that's fine, that's okay, you solve the problem. But there's many problems which are very difficult, okay? So in general, we believe that there is a scope in which you don't need to go beyond that scope to make a good prediction, to capture the distribution. And the main question is, well, but what is that scope? Okay, so this thing is useful whenever we have an intuition that you can condition on the full sentence and factors of the output. The fact to condition on the full sentence, it is very important, okay? But you condition on factors. Then if you say, well, I can actually build something that conditions on the full, then yeah, you can. Then you give up on searching over all possible sequences, but if it happens that your local scores are good, you're gonna do good. So that's, for some tasks, we observe that with neural models that are able to learn representations of sequences of arbitrary length, okay? So you will see these things, okay? I showed in the slide, how do we represent a sequence into a fixed dimensional vector, okay? So any sort of automata or RNN can do that, okay? And the question is that if you do that, unless you don't have certain assumptions, the search is not going to be tractable. That's not a problem if your model is very accurate, if all you want is to have good sequences. So there's no recipe ahead of time of one set of techniques or the other. It depends on the shape of the problem, and it depends on the actual data, okay? So because some tasks are simpler than others, so you have to. But I think it's important to know about different properties of the problems that point to different algorithmic solutions. So that's a bit, but I'm not saying that this needs to be used and not the other one, not at all. We also see combinations, and you will see them. So what people do now, they take some sort of, no, they don't do, well, they take some sort of neural network that encodes the full sentence, and then they make they make bigram predictions on bigrams, and then they use a CRF. Someone asked me this. So let's say I want to combine CRFs with LSTMs and stuff. Well, you normally put the CRF. These days, we see many papers putting the CRF on top. So you do neural things that represent the sequences, and then on top of it, you put a factored model, actually. We'll see now what is a CRF, okay? So all the combinations are possible. And it's like, whatever paper that says, I don't need all that because with greedy predictions, I do good. Okay, just wait. So maybe, yeah, they have a great result. Wait a couple of years and you'll see that then they say, oh, actually now we can improve it by combining both. So, I mean, it will depend on the problem. And then typically the tasks we use, I mean, we work on data, right? And data sets which, I mean, the real world data is another thing. So then whenever we go and run this stuff for the wild, everything fails. So we need to understand what are the dependencies, and if something can be factored and be computed locally, it is better, and then you can build up. Okay, so there's nothing. This is a toolbox. Okay, it's not a rule. It's a toolbox. Okay, so is there any question before we move on? Okay, so we're going to look now at learning, okay? And there is a very important family, which are the log linear models, okay? So what is a log linear model? So it's a model that has this form, okay? So this kind of, so up to here it's the same, okay? We have input sequences, output sequences. We have a a representation of x and y into a d-dimensional feature space. And then we have a weight vector in the same feature space, okay, such that, oh no, before, okay. So first the left side of the question, okay. Let's say what is a conditional model, okay. A conditional model is a model that computes the conditional distribution for output structures, meaning that, so the fact that it's a model, it means that there is a set of parameters, in this case W, such that if you fix this, it happens that if you give me one input, in this case a sequence X, then this model computes a distribution over all the output structures, okay? So it's a model because the same model computes conditional distributions for any input, okay? Once I have the W for any input, I have this defines the conditional distribution, okay? So that's what this means, okay? And what does it mean, a conditional distribution? Pretty simple, okay? That it means that for every possible Y, I have, if you want, a score that is positive and that they all sum to 1, okay? Which means that the scores need to, and then you can call it, we call these probabilities, okay? But, okay, and then it's very useful to have probability distributions because, you know, we can plug them and play them in different ways, okay? And the fact that we give this probabilistic interpretation will be a strong, will gives us a strong theory for how to learn this, okay? So that's why we are defining a probabilistic model. Now, so now this is the left part, okay? So you could think of probabilistic models built in different ways, okay? And now we're gonna build it with a model we call log linear, okay? That has this form. So the elements here we know, okay? Because this thing takes an input-output sequence pair, computes a feature vector, and then does a linear score. Now, so these scores are in the reals. They can be positive, negative, okay? So a log linear model, naively, is one that turns these scores into a distribution by first exponentiating, which means that any score will be on the positive side, but not necessarily sum to 1. And then we have this Z, which if you're not used to it, it's horrible, okay? That is just a normalizer, okay? So what does it mean, a normalizer? It's something as simple as if you have positive scores and you want to make them all be sum to 1, you just normalize, okay? So you sum. So we have the exponentiated score of each of an input. Z here means an output sequence. For any output sequence, the exponentiated score, if I sum them all, these loops over all possible sequence, I get the sum over all possible output sequence for this input under this model, okay? So if I plug this, I get that effectively now my scores can be interpreted as a probability distribution, okay? It is very important to understand what we're building, okay? So we're building that. Now, you could think of other ways of mapping scores in the reals to a conditional distribution, but this particular form is the exponential family, which has long history and a number of good properties and mathematical convenience that make these things a good thing, okay? Statisticians could tell you more. So that's what we're going to use, okay? So we call this log linear models. This has other forms, exponential model, this has many forms. Mach-Zehnd model is the same, okay? It's just a way to, so I will be very pragmatic and just say, I have a linear model, as I explained you in the first part, and I wanted to give it a probabilistic interpretation, okay? The model is still linear because of this. And I turn my scores into probabilities by that, okay? So I'm going to show now, first I'm going to show that this model is in fact linear and that it's just something on top of what we just saw. But essentially it's the same thing, okay? And that will lead us to a recipe for learning it, okay? Okay, so we hopefully now are more comfortable with this. Of course, here I'm summing over lots of sequences and all that. But so let's say I have this. So if I want to predict the best sequence, it means that I'm given an input and I want to predict the output. So obviously I'm going to pick the output structure that is more likely under my model. Okay, that makes sense. Okay, it's analogous to picking the one that maximizes the score. Okay, so let me go over a couple of things. First, why this name, log linear? What does this mean? So to show this, let's consider this expression of probabilities, and let's take the log. Okay, see what happens. Okay. So I just substitute here what I defined before. Because it's the log of a fraction, I can just turn it into the subtraction of the part above and the part below. And also, then here I get a log exponent which gets cancelled, so I get this thing which is a little bit more comfortable. Okay, and now they get this horrible expression here, minus log of the sum over all the exponentiated values in there. There is a mistake here or a confusion because this y. So this y is this y. We're evaluating the log probability of one y, but here we are summing over all possible y. So it should be a z, okay? But so this y is not this one. This is a mistake, okay? Or a confusion, okay? So this is the sum over the log of the normalizer, okay? So what do we see here is that, well, this is called the partition function, okay? What do we see here is that this thing, log z, is constant for, if you give x, is constant, is a constant, okay? It's the normalizer, so it doesn't depend on y. It sums over all possible y's. It doesn't depend on a specific one, so it's a constant, okay? So if I fix x, this is a constant, which means that my log score, my log probability is linear, okay? Because this is a linear form on a representation of y and my parameters. So in the log space of this probability model, the computations are linear, okay? So it means that we are modeling probabilities in the log space. It means that we are modeling log probabilities with a linear model. Okay, so that's what we're doing here. Okay, so we didn't get out of linear models. Okay, but then by having this trick of the log space, by exponentiating it, we can get a probabilistic model. So that's why I insist I'm taking my linear model as I saw before. Okay, I have this addition here, but I'm taking my linear model and equipping it with a probabilistic interpretation. Nothing's changing fundamentally. Let's say I want to do a prediction. So to make predictions, I will have to use the assumption before, okay, that my feature function factorizes, okay? Now, what I want to, I'm given w and x, and I want to find the maximizing sequence, okay? So I can substitute here. I look for the argmax y. I can substitute the expression for this. And now we said that this is a constant, okay? So it means that for any y, this is going to be the same value. So because I'm looking for the maximum y, and I'm not necessarily interested in the probability, but I'm looking at which is the best one, I don't need to compute this, okay? So I can remove this from the expression because the maximum value will not change if I remove this because it's constant, okay? And for a similar reason, I can remove the exponent because the maximum y in this space is the same maximum in the log space, okay? If I take the log, the maximum will not change. The maximum of a function doesn't change in the log space, okay? So I can remove the exponent, which I get this thing, okay? And what's this thing? It's a factored linear model, okay? So we use Viterbi to solve it, okay? So the fact that our model is probabilistic doesn't change the fact that it's a linear model. And linear models, so it's the fact that it's probabilistic and log linear it means that I'm still linear, and then for linear models, I can use, for factored linear models, must be factored, I can use Viterbi, okay? So the fact that I give this probabilistic interpretation doesn't change the way I'm going to do computations, okay? Predictions, okay? So then what is it changing? If it's not changing the representation, and it's not changing the way I do predictions, why is it useful to give it a probabilistic interpretation? Okay? Well, it's useful for learning. So parameter estimation is I have a model, I have training data, and I want to give values to the W. Okay? How do I estimate W? So whenever we have probabilistic models, what is very useful is to define the conditional log likelihood of the data. Okay? So let's look at this definition. I think I have it. There's something weird here. Yeah, so there's a typo in my slides. Something went wrong. Okay, what is the likelihood of the data? The likelihood of the data is if I have a given W, is the conditional probability that my model assigns to each of these pairs. Okay, so this should not be here. This should be a loop over from k equals 1 to m. So sorry, it's a LaTeX typo. Okay, so this loops over each example from k equals 1 to m and sums the log probability of the conditional probability that my model gives to each output value given the input value. Okay, it's the sum of the log probabilities of this. Okay, so what is in words? So the likelihood of a model measures how well this model, which is represented by W, explains the data. Okay, meaning that a good value for W, the data is fixed, and we have two W's, and we want to choose which of the two is better. Okay, so we will pick the W that gives higher probability to my data. Okay, because the data is the truth. So I want the model that is more consistent with the truth. Okay, so a good value for W will give high value for the probability of a true output in the data given the input. Okay, for all the examples. Okay, so if we are to choose between two W's, we pick the one that maximizes this likelihood. Okay, and what we're going to do is to choose over all possible W's. Okay, so we will. This is now like standard machine learning. Okay, learning is posed as an optimization problem where we look for the W, everything else fixed. We look for the W out of all possible values of W that minimizes loss plus regularization. So we want to maximize the likelihood of the data. We want to minimize the the negative likelihood. Okay, it's just a trick. So whenever we write these problems, we typically write argmin. Okay, so if we want to max the likelihood, it's equivalent to minimizing the negative likelihood. Okay, so this is a type of loss function. Okay, and this is a regularization. So this is the same stuff as any sort of machine learning. Okay, you want to have a W that explains well the data and that is not so complex. So complexity is measured with the norm of the weight vector. I'm not gonna. So here I'm using theory of machine learning. I'm not developing this. Okay, and here I'm taking the fact that I can give to my W, I can give a probabilistic interpretation. So the fact that I can give a probabilistic interpretation defines the likelihood. So I can say that I want the max likelihood model. Okay, so if everything is linear and so on, so if I'm using linear models, and that goes back to linear and nonlinear and all that, then these problems is convex, and we have guarantees that gradient descent will find the optimum. But now, I mean, then this is not, this is just a way of modeling learning. So maybe the loss is, maybe these two things are just not the best way to find the W. So maybe it's better to use the nonlinear and other things and then solve the nonlinear. That's something that of course, can be changed. But under the framework of loss and regularization, it's kind of handy then so it's kind of handy in the world of machine learning and modeling to just think about loss functions and regularization. And then if it's convex, we just don't need to think about that. I mean, there are recipes that will solve exactly that. If we model our learning problem as a non-convex problem, we not only need to think about the form of the model, the type of loss, and the type of regularization, but we also need to think that the optimizer we use will not get stuck here and there. So it's just more difficult, okay? So then you can go and solve more difficult problems, okay? This is easier to solve, okay? So if it works well, that's okay? But again, so this is where I connect with machine learning, okay? I'm not going to go deeper in here, but I'm gonna still discuss things that have to do with this loss and the tractability, okay? And so I talked about factor linear models. I described that these models can be interpreted probabilistically as a log linear models. These log linear models define the log likelihood, but still there is a tractability issue that I will show now that has to do with, it appears in several different places, but one prominent place where it appears is the computation of this gradient, okay? So to make these things tractable, to make the computation, so of course, to do this, you to gradient descent, you keep computing gradients and so on. The problem is convex, but you still need to compute the gradient, okay? The fact that it's convex doesn't need, so in order to make this tractable, okay, there needs to be some assumptions, okay, of what's the model, okay? So there's two common things to use that are, this is more of an historical remark, but I think it's useful I'm going to present that to you. And so you can define a local loss and you can define a global loss. And so this global loss is what is called CRF, okay, conditional random fields. I'm sure that many of you have heard about that and have used them and have studied them, okay? So in this framework, one way to describe CRFs are log linear models that use a global loss. And I think that the concept of local and global loss is an important one, okay? So I'm going to describe it now quickly what this means, okay? So in this way, we know what is a CRF versus a local loss and things like that. So maybe I'll try to give you a picture of how that works. Okay, let's start with the local one, okay? This was proposed even before, but McCallum, Freytag, and Pereira in year 2000 proposed something called Max-End Markov models. So Max-End is kind of the same thing as a log linear model, even though it has to do with the loss function. So it's kind of trying to optimize the log likelihood. And Markov model is another way of calling factor model. I prefer to call factor linear model because it's more of an extension of linear classifiers to structures, but you can also start with HMMs and change it, okay? It's all the same, okay? So these things have different names and depending on the, okay, so, so we have a distribution of full sequences, full output sequences given full input sequences. What we can do whenever we can, because this is a probabilistic model, we can apply the chain rule, okay, and say that this is the same as predicting, given the full input, predicting the first tag, and then predicting the rest, given the first, okay? And you can unroll this to just have a product of terms that predicts one tag given all the previous ones, okay? So these equalities are exact, okay? This is applying the chain rule. And here, from here to here, there should be some sign here that shows that this is no more exact. There is an assumption that says that the difference is here, that says that instead of conditioning on the full prefix of the output, I just condition on the last symbol, okay? So it's some sort of factorization, okay? But so the underlying assumption is this one, okay? That the probability of one tag given the full history is the same as the probability of one tag given just the previous one. Another way to see that, the assumption is that given the previous one, the current tag is independent of the rest, okay? There's no information in the first tags that is relevant for the current tag if you already know the previous one, okay? This is what this means. So if we believe this, and this is an assumption, it's something we believe in, we can make this thing, okay? So instead of, I've been talking quite a lot of building distributions from sequences to sequences. If you take this assumption, you can now break it down into distributions that are like that. So this is what we call a local distribution, okay? So we take that the probability, the distribution of sequences breaks down into product of distributions of one tag at a time, okay? So, which means that the log linear model is normalized locally, okay? Because what the distributions that, the things that we need to learn now are these things, okay? Is the probability of a certain tag given the previous one, okay? So you're gonna do the same trick above, but it's not a sum anymore. We just have one tag given the previous, so we just represent the bigram, okay? And here now we normalize locally, okay? We sum, instead of summing over all the sequences, we sum over all possible tags at that position, okay? So we call this locally normalized, okay? And because the model is locally normalized, the likelihood is also local, okay? Before we were saying, my model assigns probabilities to full sequences. And now we say, yeah, it assigns probabilities to full sequences, but it does so by making products of probabilities of each tag, okay? But the probability of the sequence is just the probability of the tag. So the relevant prediction is this local distribution. So we can turn that global loss into this local one, okay? Because by making use of the assumption. So now the likelihood is looping over all the examples and looping over all the positions in the example, and then trying to maximize the fact that the current tag should have the highest probability, okay? Or the likelihood is the probability that the model assigns to each tag, okay? So the notion of locality is that instead of computing this distributions over full sequences, we go one thing at a time. So if you do gradient descent on this, you'll get that the gradient has this form. Don't worry, I will not expand on this, but normally when you do log likelihood, you have that the gradient has two terms, the observed and the expected. So by taking this assumption, so these things are easy to compute, okay? There's no loop here, so while this might be kind of might be difficult to understand here now during this lecture, this is just a standard max 10, or this looks like multi-class classification in sequences, okay? It's because at each point we're predicting the tag out of a set of tags. So the expectation runs over the set of tags. That's the important thing, okay? So I just note this and recall that if we believe that that we can break down our distribution like that, then everything looks pretty straightforward, much like multi-class classification, okay? So what is the opposite? The opposite is just not using that assumption, okay? And that was proposed a year later by almost the same authors, Fernando, who was here giving the talk, and Lafferty and McCallum. So they proposed this conditional random field, which is a log linear model with a factored log linear model that predicts, as we saw, and that directly focuses, optimizes using the global laws. Okay, so we call this global because it works at the sequence level, at the structure level. Okay, so here we're saying my model assigns, computes distributions of sequences, and I'm just having these laws. Okay, not that I'm doing one thing less as before. Before I was further decomposing this, and now I'm not doing that. So what's going to happen? What's going to happen is that if I pose the problem is convex, so I can say, give me the W that optimizes these laws and regularization, okay, and the same. And then the optimizer will say, okay, give me the gradient, okay, and you'll see, here's the gradient, okay. So the gradient, as any Maxent or log linear model, is a sum over examples of some observed thing minus some expectation, okay. So it's observed. Look at this. These are observed features at every example, right? The features extracted from the true output minus features, the sum over possible output values of features extracted from this thing. And this is an expectation because it uses the current model to weight that, okay? So it's a weighted feature vector, which is weighted by the distribution we're learning, okay? So the gradient says that, okay, that you should keep doing this type of updates. And the problem is that, so there's two terms here, the observed and the expected. The first term is easy to compute. It's just you take each example and you compute the feature vector like that, okay? This is given, this is given, this is given, this is given. There's no problem in computing that, okay? All is given. But the second term involves looping, computing the expectation over the output space. And the output space is exponential because we are in structure prediction, okay? So in order to compute this, so conceptually, we go over each output structure and compute the probability and compute the feature vector of that, okay? We compute this expectation. So conceptually, we need to make this computation, but we need to sum over all possible sequence. So we cannot do this in brute force, okay? So, but of course, there is a solution, okay? So the solution is based on the forward-backward algorithm, okay? And it will make use of the fact that our feature vectors have this factored form, okay? The fact that our representation is factored, at the beginning of the first part of the lecture, the fact that our representation was factored was critical to make the computation tractable, the argmax, the prediction tractable. And now when it comes to probabilistic learning, the fact that our representation is factored will be critical to the fact that we can compute the gradient, okay? So the solution, which is a bit math heavy, so I'm just gonna go high level, involves defining a quantity which is called the marginal probability, okay? And the story is that this expectation that loops over all possible sequences can be rewritten as something that instead of looping over all sequences, it loops over all positions and it loops over all the assignments of output tags in that position, okay? So again, it's exploiting, so this is, we're looping over bigrams at certain positions because that's the factorization I set up. I'm working with bigram factored models, okay? So depending on the factorization, you'll loop over all possible factors in a certain input, okay? So we can rewrite this expectation as instead of looping over full sequences, looping over factors, where now, okay, this quantity will be expressed as the probability of this, the marginal probability of the factor, AB at position I, times the feature vector of that factor, okay? So what is the marginal probability of this, okay? So this is the marginal probability of having labels AB at this position, okay? So it's given, I have a model that given an input sequence, I want to compute what's the probability of observing not a full sequence, but just a part of it, okay? So how I define this is by summing the probability of all the sequences that have this factor I'm interested in, okay? And so this is a definition. So once I have marginal probabilities, I can plug them in here and compute the expectation, okay? So the question is, how can I compute these marginal probabilities, okay? So to recap where we are, and before I just, so the next slide will just we just show what's the recipe of forward-backward, but to recap where we are, so what we're doing here is we're again taking advantage that probabilistic models can be used in many different ways. So the standard thing is to define probability of sequences given an input. But you can also define marginal probability. This is a standard from any probabilistic class you've been, okay? You can ask for the probability of a part of your output, and you obtain that by summing over all the output values that have that part of interest, okay? So the trick behind this equivalence, which is not obvious here, this equivalence is not obvious, the way you turn this into this is by taking advantage that we're using a factored representation, so it is the same to loop over output structures and have a representation that sums over positions than looping over possible factors and get the representation of that factor, okay? There's this equivalence, okay? Again, this uses linearity, this uses factorization, and it uses linearity. So these two components, factor linear models, are essentials to this. If you give up on that, you lose these properties, and so you lose convexity, you lose things like that, okay? Okay, this is a bit intricate, okay, these long equations, but the fact is to motivate the fact that these things are, in order to derive all these methods, you need to get, these intricacies between computations and what you want to compute and how you're going to compute it, okay? So we can reduce now computing gradients for a linear model as expressions that use these marginals. So the last part to close this is, well, how can I compute these marginals, okay? So this is going to use the forward-backward algorithm, okay? Again, there's long equations here. I don't want you to be obsessed with these equations. The high-level picture is that, well, I'm going to use a little bit of rewrite, as I did for the Viterbi algorithm, okay? Now, I have a fixed input and a fixed W, and for convenience, I'm going to write the score of a certain bigram at a certain position as the exponentiated linear score, okay? Why do I do this? Because if I do this, I can turn this expression, which uses the features and the inner product, into something that is just a product of scores. How do I do this? It's like this is an exponent of something that is a sum over positions, okay? From here to here, this is f is a sum over positions. This is factored, and because I have an exponentiated over a sum, I can turn it into a product of the exponentiated terms, okay? So I can turn the expression for probabilities into a product of scalars, okay? Such that, and this is where it comes, such that now this z here is a sum of products, And the marginals is also a sum of products. In this case, it's over all the sequences. In this case, it's over all the sequences which have a certain factor, okay? But the fact is that I'm reducing my problems of computing marginals into computing sums of products over an exponential number of elements in the sum, okay? Sum of products. So whenever you have sum of products, you can use forward, backward. I'm not gonna go into the detail of this. The algorithm is analogous to Viterbi in the sense that you have to. So in Viterbi, we are interested in the max over sequences, where by each sequences we do sums, and here we're interested in sums over sequences, where for each sequence we do products. Okay. So these two problems actually are related to the theory of semi-rings. I think that Noah explained that a little bit. The short story is that we can write dynamic programs that can compute these quantities, you know, by having a dynamic program that, you know, that defines forward and backward quantities that are extended along the sequence, and then you can compute these things. I don't think I have a quick way of explaining how you define the Z and the marginals using these equations. So there's two cases here. Those of you who already have studied this and then could catch up with my notation and then make sense out of that. And then those of you who have not looked at forward, backward, and then it's just impossible that now I can explain you that. The important fact is to understand why we need certain computations, and then understand that and then know that those computations are solvable. And then you can go and then look at the mechanics of that algorithm and why that works, okay? But in the context of this lecture, I prefer to keep it like that. So similar to Viterbi, these kind of recursive quantities can be computed in linear time times the number of tags exponent to 2, okay? And then again, this 2 is the number of tags we have altogether here, okay? So the higher the factorization is, the more cost you pay, okay? This said, I do really recommend you to look at the mechanics of Viterbi and forward, backward, and the million generalizations that have been proposed, because for those of you who are interested in applying these things to slightly different problems, you might have to actually work it out, okay? You might have to actually work it out to take advantage of something of your problem. So, and by the way, it's not so difficult, but it requires you looking at it, okay? Okay, so I think that that's it for CRF, which it's something, right? Okay, so this is a summary slide. Yes.
So if I choose to factorize differently, could you go back once? Oh, it doesn't matter actually. That's a formula. So if I choose to factorize differently and I don't condition on just yi minus 1, but I also want to have yi minus 2 maybe?
Yeah.
Or is this becoming practical? Or maybe I even want to go to the future, I don't know. So when
So to the past, so there's no past and future here. There's no past and future here. I don't have any past and future. I don't. So this is the summary slide of what's the CRF, and I don't see past feature. So I just have. This is important because I don't have any. I'm not telling you how I compute this. Okay, if I compute this left to right, right to left. So this is. My model produces a scores for every bigram and position. Trust me when I say that I could have defined my bigrams differently, says that this is I and yi plus 1. So this is just, I mean, you have to fix one thing and then change forward, but the models are equally expressive, okay? That's first thing. So in these kind of things, there's no past and future. The future, let's say, the relative to position I, the bigrams that are to the right of it affect equally to the bigrams that are to the left of it. This is precisely what we are doing. We're we're moving away from greedy methods that predict left to right or right to left, okay? This is undirectional. This is undirectional, okay? Then the second question is, how can I add more tags? Yeah, you can, and that's the price you pay, okay? Can you, so do the tags need to be contiguous? For these things to extend easily, yes. But there's non-contiguous versions, yes. And then, what's the best, is there a universal order of the size of the factorization? No, okay? That depends on the problem. Actually, for many years, the methods for this task I'm talking about, for a certain data set, which is not the real world problem, classifiers that don't do any viterbi or anything could obtain the best results because the features were very good. I mean, if the features are very good for that data set, and you capture that, I mean, you don't need any of these. But for example, for parsing, where the output structure is a lot more intricate, it is very hard to solve. So it is very easy to solve name entity extraction with good classifiers and good feature engineering. It is very hard to do the same with parsing. With parsing, you take advantage of these frameworks, okay? And so if your structures are complicated, you'll need some of these, okay? Other questions? Please. They are the best parts, your question. Okay. So the summary is that we use probabilistic model, which points to a loss function. Then all this is, because it's linear, we use gradient methods. There's all these solvers. This is very easy to use. In Python, you have LBFGS in SciPy, but there's all these. So there's general solvers like LBFGS. There was also a lot of work in machine learning and NLP of specific solvers that take advantage of the fact that we are dealing with CRFs that normally deal with very sparse things. So there were solvers specific for that. So if the problem is huge, this might take some time. So you know, that's a lot of stuff, okay? But the point is that this factorization leads to tractable computation, be a forward, backward, okay? Or any other algorithm depending on the structure, okay? All right, so just let me give some discussion before we move to the next topic. It's like I give you local models, sometimes called MEMS or CRFs, and then at the beginning we were talking about HMMs or CRFs. It's like, what's all that? I mean, they're all probabilistic. It's like, so let's see if we can recap, okay? So as a kind of my framework goes top down, okay? The way I presented this is top down. So I started with linear models, and then I gave this probabilistic interpretation of a linear model, and then actually I worked a little bit more for this one to say that this family of models is actually a particular instance of these ones that makes an additional assumption that the distribution at the sequence level is just a product of distributions, okay? So the important part, it is very important, in terms of expressivity, it is the same model, okay? Because both type of models use the same factorization, okay? And same thing for the prediction. They both use this kind of thing, okay? This is a consequence of using the same factorization, okay? You can see here that the representation, in both cases, the representation is the same, okay? But this sums over positions and exponentiates, and this evaluates at each position and makes the product. But because there's this equivalence between products and sums, or one with exponents, it's the same. Okay, so the only difference is not so once the model is trained, it's the same. So the only difference between these two things is at training time, is the loss. Okay, so it's the same class of predictors, but you choose to learn to train it with one loss or with another loss, okay? So, and this we still see today a lot, okay? Are you using a local loss or are you using a global loss? I don't know. So what's the advantage, okay? Well, the local loss assumes certain things And then it's very easy because you get rid, by this assumption, you get rid of the structure. You get rid that you are dealing with sequences or trees or that. So you have an assumption that lets you decompose your distributions into distributions that are, let's say, multi-class style, okay? And then the computations are very easy, okay? And also you can treat different parts of the sequence independently, so you could parallelize better, okay? So there is an advantage. There is always an advantage of being local, okay? If a model can work locally, because someone told you that beyond the scope of locality there's no information, just use it, okay? It's a waste to model global stuff if things are local, okay? So it gives us an advantage, okay? But it is not the case. So there's something called the label bias problem that is all the things that can go wrong by doing this assumption instead of staying here, okay? So this is to the fact that, so again, I'm using an additional assumption for using these laws, which means that the model is more constrained, okay? It's more constrained. I'm not going to go into explaining exactly what's the difference, but it's more constrained. So there's less chances that there is a good model in that constraint set, okay? So CRFs are more relaxed, and then we've seen papers of everything. So then it's all about, okay, this theory, it's certainly an important theory, okay? The message is that, so there must be some scope where things are local, but which one it is, okay? And how do you find it? Should you find it by some intuition, so you encode it, or should you design methods that find that, okay? So these methods that find the scope of things normally are very hard, okay? They are computationally hard. So do I take this assumption or not, okay? So then all this is the theory. And then in practice, people have to compare these two losses, and in some cases, people have observed under this representation, the global loss works much better. And sometimes there are astonishing results that it's really much better, okay? There was a paper, I think last year at ACL, on parsing, showing that global loss could still help a lot. But actually this year, there's lots of papers that have very rich representations of the input, and they use a local loss, and they happen to work better than the other ones. So it means that, you know, if your representation is a good one, you suffer less from structural things, okay? So there's always a trade-off, okay? The questions are a bit more intricate and more advanced, and I'm not going to go over it. But I don't think it's something that this will never be solved. This is a trade-off that exists. And the thing is, whenever you have a certain problem, understand what are the trade-offs and move here or there. Okay, so I think that's why we call this more of a fundamental thing. But you'll see papers that say, yeah, we do local, even though we can suffer the label bias problem, but we don't seem to observe it because our results are better than those that model the label one. Okay, so, but you know, data is data. Okay. So this kind of reduction to multi-class learning, and this is also easier to extend to more complicated structures. Okay, HMMs. So HMMs, what's the difference between an HMM and a log linear model of this type? So essentially, an HMM models the joint distribution of X and Y, while what we saw now models the conditional distribution of Y given X, okay? So if you work it out, in principle, these distributions are contained here, okay? You can always decompose joint distribution into a product of conditional ones, okay? But that's just probability theory, okay? What matters is the modeling, okay? So the models are not the same. So what matters is the expressivity behind the model. So, sure, HMMs model the joint, which in principle contains the conditional, but they model it using some assumptions, and they model it having this type of parameters. So starting parameters, transition parameters, and observation parameters, okay? So the architecture of the parameters is tight. You cannot change that, okay? Because if you change this doesn't work, okay? So by computing things in this way, sometimes called stochastic methods, very simple stuff. This is very old, from the 60s, okay? So things are as simple as max likelihood and all that, but it's very tight. So actually, one question is, what's the relation between an HMM and a factor linear model, okay? Are they very different expressively? So I think I'm gonna skip this because I think I gave a lot of things. But the point of these slides is that actually HMMs, which are written like that, so CRFs or factor linear models are written like that, okay? A factored representation and a weight vector, and the prediction rule is an argmax like this. And an HMM is written like products, okay? But I can actually change these in equivalent ways. I can do manipulations that where actually I can write an HMM as this, okay? I will not go over this now. This is the solution, okay? It's like a puzzle, okay? It's like, how do I design a set of templates and the corresponding weight such that if I'm given an HMM and I use this thing is equivalent, okay? This is the puzzle, okay? But so the answer is yes, like this. I'm not going to explain that now. But the conclusion is an HMM is a factor linear model, okay? So means that in terms of expressive, so it's this particular type of such model, but factor linear models, the way we have defined them, I didn't say the feature templates need to be like that, okay? You can, depending on the task, you can write them, okay? Or you can train a neural model these days to compute them for you. You can do that, okay? You can pre-compute a representation and plug it in here, and then train a CRF using these neural representations. You can do that, and people do that, okay? So nothing will change, okay? You can do that and use an existing CRF implementation, okay? You don't have to change a single bit, okay? While for HMMs, the underlying feature templates are hard-coded, okay? So we are stuck with certain feature templates that in many cases we don't like. In many cases they are good for what they were designed, but they were not designed for other tasks such that discriminative classifications like what we do, okay? So in terms of representation, the HMM feature templates describe a generative process and are fixed. And CRFs, they are designed such that you don't fix ahead of time the features, you just fix the signature of the features. You say, give me feature templates, and the rest is already solved, okay? In practice, what happens is that good features are very good. So in practice, what happens is that most tasks we look at are discriminative. So feature engineering works very good. So in the last decade and these days, we see that by working on the representation, and so things improve. And so before we were doing feature templates, and now there's this whole field about representation learning that plugs into this, okay? So you want modular stuff, okay? But you'll see that there are CRFs which use representation learning for the features, okay? So you don't have to change much, things plug by itself, okay? Another thing is the parameter estimation, okay? So that's representation. Another thing is parameter estimation. So HMM learn the generative. So they model both X and Y, while CRFs model the mapping from X to Y, okay? So this distribution contains this one somehow. So what is better? It's better one or the other. Actually, as far as I know, in machine learning, this is a question that is not fully solved. Ideally, it's better to have a generative model because it includes this one, okay? And a generative model also allows makes it very easy to have combined objectives that use supervised and unsupervised data. And so there is a lot of advantages to modeling the generative one. But if you're gonna do is to be evaluated in terms of the mapping, so Vapnik, the inventor of SVMs, came in the late 80s, early 90s saying, if you want to do well on the mapping, focus on it and don't focus on this. This is a much harder problem, okay? Modeling two things, it's harder than modeling one. So, so you can look at the papers and see, well, these discriminative models are much better than generative ones, okay? Which means that discriminative losses are much better than generative ones. I don't think that is true, okay? What is true is that for discriminative methods, we can have, it's easier to have very flexible representations, and good representations give you a better boost at discriminative tasks, okay? But it's a bit like that, okay? But to me, open problems, okay? All right, any question?
Can you elaborate a bit more on why the generative models are better at unsupervised tasks than the discriminative ones?
Well, unsupervised means that you don't have labels. So it means that I mean, if I don't have labels, I cannot model a mapping. So I don't have Ys, okay? So this is not. It's not clear how do I evaluate against. While what I can do, that's actually HMMs have been used like that. Where I had the picture of HMMs. I don't have it here. While you can design a discriminative model like an HMM, a generative model like an HMM that has sentences and states. So I think that Noah mostly focused on the case where the states you supervise them, but the HMMs were originally designed to learn the states. Okay, so you can define a generative objective that computes certain states that generate words, and you can try to make that those states are similar to quantities you want. So you can make a generative model of X and have some structure in the model that is similar to what you want to predict. And in that case, you could have a combined objective that says, I have some inputs with Ys and some inputs without Ys. So the probability of an X is by summing over all the Ys. Okay? If I have a model that predicts X, so if I have a model where I have an equation, okay? So if I have a model like that, and I sum over all Ys, I get the probability of X, okay? So I can have an unsupervised objective that maximizes the probability of X by summing over Ys. And maybe for some X's, I do have the true Y. So I can have a model that if I have the true Y, it only sums over that one. While if I don't have any Y, I sum over them. So you can see those things. So that's a generative objective, okay? Because if you don't have supervision, you can only learn to generate the data, okay? So you can find examples of those. Yep.
I didn't forget about the label-based problem for this MEMM. Could you explain?
Yeah, I didn't elaborate on it. I didn't elaborate. Don't make me do that. The origin of this is the fact, so the fact that, so here the normalization is global, okay? And here we are forcing that at each position this thing normalizes. So at each position you need to make that the scores sum to 1. And the other, you don't need that. You just need that all the sequences should sum to 1. So you can, the elaboration for that, the conclusion is that there is a huge, the bias means that whenever, for certain positions, that have only a few next labels, whenever the transitions just cover a few labels, those things have a much better, so the model gets biased towards those as opposed to cases where the distribution is more uniform, okay? So these models have a hard time of weighting cases where it's only 1 or 2 values that are likely versus distributions over the possible values that are a lot more uniform. In the way that when you put them within the argmax, those things that have less output values get a weight that is unreasonably large and dominate the computation. So that's why there is a label, it's a bias towards cases where there's only a few labels that are seen. You can see that. You can check the papers. Okay. Okay. Let me go over this. I'll try to be high level. I have 50 minutes. Okay. All right. So don't worry. It's going to be simple now. So we've seen linear models. We've seen all these probabilistic things and all that, likelihood maximization. You have to compute gradients, but then you have to run forward, backward, and all that. It's like, can we not learn W more directly, focusing on mistakes? Okay, because there's like a very simple paradigm, like, well, you just have a W. If you do a mistake, you just correct it, and if don't, that might be good. Okay, so can we just not do that? And the good answer is yes. Okay, so and also it's like, I never showed an algorithm, right? I only showed equations. It's like, can you show me an algorithm? It's like, actually I can, because it's pages and pages long, and I would have to introduce more notations. Like, there's no pseudocode and nothing. Okay, so that's the magic of perceptron, which is an algorithm that originally designed for online settings, but used for batch settings. So you have a certain W that represents a classifier or a model, and you keep running it. You visit examples. This is true y for x, and you compute your best prediction given your model. And if the prediction is wrong, you update in this way. Okay, this is the perceptron update. Okay, so the properties of this is that if you do this update, where you add the representation of the true output and you subtract the representation of the best prediction given your model, then it happens that at the next iteration, it is less likely that Z is the argmax. So Y, it's going to be more likely to be the argmax. So if you keep running this, it will converge. Okay, so this is great because actually this is the full code of the method. Okay, so so is this for structure prediction or is this for classes? So what is here that is? So this looks like classification to me, right? There's nothing that looks like structure prediction. So what changes in structure prediction? What is the element that is different in structure prediction? X and Y are sequences, okay, but
Z and Y are high-dimensional.
huh?
Z and Y are high-dimensional.
They are high dimensional, but the main problem is these argmax, okay? So because there's an exponential number of z's, these argmax might be tricky. But we know the solution, right? We just use a factored model. So it's not a problem if f is factored. I'm not writing here that, but if f is factored, this is structural, okay? So it turns out, and that's yet another advantage of using linear models and factor methods, that this algorithm that, so Mike Collins in 2002, he took the multi-class perceptron and said, well, this is an algorithm for structured prediction too, because, I mean, you look at the theory of underlying the perceptron, and I mean, as long as you can obtain, so it works for linear models, for any linear model, and it only requires to obtain the max one, okay? The max value of your, according to your model, okay? If you obtain the max, if you update with respect to the max, it's gonna converge and it has good generalization properties, okay? You go to the theory, there's nothing that says, but this will not work for exponentially many. No, no. The only thing you need is to be able to compute it, okay? The statistical properties remain the same. So this is another advantage of that. By working things as an extension, we extend it, but we can still make use of the theory designed for binary and multi-class classification, okay? So this is great. If you want to generalize better, that is trick of averaging. Again, is a trick designed in multi-class. It works equally well. It's about, instead of keeping one weight vector, you keep two. You do the updates that are the same in the same way, and this second vector you keep summing, okay? So it's some sort of average that that it's like some sort of combination that is given by averaging, and this has a number of properties. So it's orthogonal to structure prediction, but it gives a high weight, okay? It is actually nice to look at in structure prediction to analyze what's going on, the mistake driven, okay? So let me just illustrate this, okay? So we have a sentence, we have a true output, and let's say that Z is the output that my perceptron predicted, okay? I'm just gonna, so I'm just using a little assumption that is satisfied in practice, that the prediction of my method, of my current method, is not going to be totally wrong, okay? It's more or less, so let's say we train it for a while, okay? So it's not going to be totally incorrect, okay? It's going to be almost correct, but there will be one mistake here or there, okay? So the difference in structural prediction is that we're predicting sequences, okay? So parts of the sequences will be okay, and maybe there's only one tag, okay? Well, it still counts as a mistake, okay? But what is going on, okay? So let's look at the update, which is it's like some form of gradient. That's why I call it G, okay? But the update is like take the feature vector of the true Y minus the feature vector of the Z, okay? That's what perceptron says. Now we know for convenience and tractability that actually we build this with a factor model. We know that these are aggregations over running a feature function over the sequence, right? So I obtain it by summing over positions with respect to Y and summing over positions with respect to Z. But what happens if there's actually a lot of overlap between the Z and the Y? What happens is that even though there's 1, 2, 3, 4, 5 factors for each of the solutions, actually most of them cancel because everything, all the bigrams here are the same. So they will, the one of the Y and the one of the Z will cancel. So in practice, the update, whenever there is a mistake like that, the update will only affect the features that have to do with the bigrams around the mistake, okay? Which namely are these ones and these ones, okay? So I'm gonna, for position 2, I'm gonna add person, subtract person location, add person nothing at position 3, person nothing, add, and subtract location nothing. So what is the effect of this? The effect of this is that, okay, this is with respect to the 5 plus 5 feature vectors that were here originally, from 10 feature vectors, I only get, so most of them cancel, so only 4 make it to the gradient, the others get canceled, okay? And if it happens that each of these feature vectors is actually sparse, which it is. In the way we constructed our feature space at the beginning, it is very sparse. It happens that the perceptron updates are typically not sparse. They are really very, very sparse, okay? Because they only focus on the mistakes, okay? So even though perceptron is not explicitly regularized, it's something that produces very sparse feature weight vectors, and that's a very good property because perceptron is not only quick, it's not only simple and quick to train, but it also produces weight vectors which are very light. They're very sparse, so that's good. Yeah, this is some remarks, like perceptron is an online algorithm. Sometimes it works much faster than batch ones. So SGD can be thought of a more clever version of this. So SGD is very popular. So SGD and perceptron share many of the flavors, okay? So that's the theory. If we have linearly separable data, it will find it. You can explain, so that's the convergence in the training. Then the really good important part is how we generalize to unseen data. So again, using linear properties, you can do something related to margin. There's all these generalization properties, okay? Here's on a parsing task. So here's after doing an epoch of perceptron through the training set, here's the accuracy we get on development data, okay? Not on the training, on the development, okay? So you can see that after just parsing, after just doing one pass, so the best performance is maybe close to 92, but really after just a few epochs, we already see how that method will work, okay? So I set up some features, and then I run perceptron, and I quickly see the performance of those features, and then I change them, and I quickly see whether one is better than the other. So it's very handy, it's very quick. Okay, and now there's SVM, but I only have 4 minutes, so I will skip this. It's more equations. Okay. It's just like, so SVMs are like perceptron, but with a notion of margin. Okay, so in structure prediction, you can also have a notion of margin. Okay, I will skip this. Okay, what a relief. Okay, so the summary is that I presented these linear models, okay, that they employ factored representations, and then they do argmax. Okay, so I showed all the lecture, label bigrams factorization. Decoding, which is solving the argmax, is done using Viterbi. Computation of marginals, which has beyond gradients, it has many, many uses, okay? It uses forward, backward, so there is all these advantages of all these relations between factored models and tractable computations of different forms. And then whenever we look at parameter estimation, which are methods and algorithms, they will, in some way or another, will require those computations, okay? So structured prediction is where we extend machine learning for multi-class in such a way that we can reuse as much as possible, okay? So we have to take an assumption here and there to make it work, okay? There's, as I said before, there's a lot of methods for, once you have everything defined, there's a lot of methods for quick optimization. Here are some references. There are more, but here are some. I will not comment on that. I do want to make a few slides for closing of what can we do beyond all this, okay? So I mentioned, so one thing you can do is still do sequence prediction, but attempt to do, instead of factoring on bigrams, factoring on bigger chunks of the data. I think that over the lecture I said this several times, and when I presented Viterbi and forward backward, I showed this exponent has to do with that, okay? So in general, we can do that. I mean, we can extend, let's say we take every chunk of K labels, and then our feature functions are more expressive because they take this chunk, and then we have to extend this. So in general, you can think of notion of deterministic state, if you're familiar with finite state machines, and all these things can be worked out, okay? So what is necessary is to extend the Viterbian forward-backward in the corresponding way, which then will run linear in the length, but exponential with this size, okay? So there's many variations for this. Actually, for example, if you take post-tagging, most accurate post-taggers for a long time have used trigram factorizations, okay? So if you go from bigram to trigram, you get huge gains. From trigram to higher order, people haven't found that much of a gain, okay? That's for factored linear models, okay? If you take parsing, so parsing, okay? So parsing, it's like, okay, what if we don't predict sequences, okay? So we want to predict trees. The game is going to be the same, okay? It's going to be, I break down my global structure into factors. So tomorrow Yoav is going to talk about dependency parsing, which are trees which are built of these edges. So you can say, well, a parse tree is a collection of edges. My factors are these edges, okay? So I'm going to have edges are this form, and I have features that represent edges. And now I have a routine that computes the best tree given scores for each edge, okay? And then you just plug it in, works, okay? You change the prediction algorithm, but same things work, okay? So as I said, then these things can also be extended to higher orders, and we have observed that higher order models for parsing are very important. So in general, if we focus on linear structure prediction, we can think of sequence prediction. We can have parsing. In general, if you have structures Y that are not sequences nor trees, but are something in the middle or something more general, as long as you can enumerate parts, you can try to build this framework, okay? So it's like I have structures which decompose into parts. I define features on parts, and I define a way to build, to find the best structure given scores on parts, okay? I want more expressive models. I make my parts bigger. And I see that, or smaller, okay? So you things like that. But you have to work out the algorithmics, okay? Do this thing needs to be exact? No, there's also work that show that under certain conditions, if you only find these approximately, learning is also possible. So there's been all this work, okay? But of course you lose some. So if it's not exact, you lose some guarantees. But it's not completely impossible, okay? So, and now, of course, nonlinearities, okay? So when you think about nonlinear models, there's still one main distinction, okay? Because we've used linearity in a number of ways today, okay? One important part was that the score of a full sequence is just a sum over scores of the parts, okay? So that maintains linearity, okay? But each part has a score. So I said, today we saw methods that all I talk about is that this score is given by a linear model, okay? Which means that, and because this maintains linearity, it's like my scores of my input-output structures are linear in the weights, okay? But I could still have a factored model with nonlinear scores, okay? So you can compute these scores with some neural network that just takes the input, let's say a sequence, and a certain position, and computes some vector. So people do this now with by LSTM, okay? You run an LSTM left to right, and right to left, and for each position, you get two vectors. You put them together, and you get a feature representation of a position of the sentence conditioned on the full sentence, okay? That's given by the LSTM, and then at that position, you try whether the bigram is a good match for that position, okay? And to make sense for these bigrams all together, because these bigrams overlap, bigrams of outputs overlap, you can run a CRF on top of it and and work. Or here, this is more an expression of a feed forward, but I mean, who cares? I mean, there's all these options, right? The fact that is that factored can be still combined with non-linear, but you lose a number of properties, okay, which I think I highlight, okay? And then you can do fully non-linear and fully non-factored, okay? So then nothing is tractable, but doesn't mean that it will not work, okay? Because greedy sometimes works depending on things. So here you have an input, and you compute some hidden representation, and out of the hidden representation, you compute the output. And then it's just impossible to optimize over everything. It's impossible to have some convex definition of what's the best way to map this to H. So that is just not possible, but still people deal with these non-convex problems, and they seem to be quite practical also, okay? So that's also possible, okay? So, but some notions of what we saw today are still apply here, okay? Still apply, okay? But this is the picture of things today, okay? And I think that that's it. Thank you. Yeah, if there are questions.
Time for a few questions. No questions. So maybe everybody's hungry. I don't know.
Yeah, well, there were lots of questions, I think.
You already have questions.
Okay, thank you.
Thank you.